Okay, good afternoon. I don't see anybody connected online, but I think this is not a problem. I checked on the old channel and the new one. I think you got an email this morning from me. I gave you the link of the new room. So just in case you want to use it, and also for communication, you can use the chat in that room. So it may be useful for exchanging information, documents, or whatever. Okay, if you don't have any question on the previous lecture, I think I can move forward. So, let me share the screen, otherwise we don't see in the recording what we are talking about. So, today I want to give more details on coastal hydrodynamics and morphodynamics, which means more details on the models that we use in order to study the evolution of beaches. We discussed the importance of beaches and discussed the importance of predicting their evolution. So predicting also the impact of human disturbances, the impact of climate change. And in order to do that, I mentioned that the usual way in engineering to predict the evolution of a system, whatever it is. A system may be a building, may be a river, may be a beach. The usual way of predicting the evolution of the system is to write a mathematical model, to write a model that describes the evolution itself. And through the model, we may derive a prediction of what the future will be. Of course, in response to assigned forcings. And the forcings can be natural, can be human-induced, can be climatic, of course. So this is quite usual in engineering. And this type of approach is called a deductive approach, which means that we try to elaborate a deduction through a mathematical model. There are alternative approaches in engineering for making design. The alternative approaches may be empirical, may be based on our experience. So it is not strictly necessary a mathematical model in order to elaborate a prediction, in order to derive the design variables for a given project. We may also elaborate a kind of a guess, basing on the so-called expert knowledge, basing on our experience, basing on our personal feeling about the system we are studying. This is something that it is very useful. It is very useful because it is based on your expectation. It is based on your rational understanding of what's going on. So when it is the case to use a model or when it is the case to use some empirical prediction, some expert knowledge, let me say that in my opinion, we need both. We need both because in both cases, you have uncertainty. You have uncertainty in the design, which is usual in engineering. Whatever you design in engineering, there is uncertainty. And we need to manage this uncertainty. This is a usual job for engineers. Engineers are used to manage uncertainty. And in my opinion, but not only my opinion, it is a classical approach in engineering. The best way to manage uncertainty is to combine methods, to combine estimation methods, to combine design methods, and then see how they behave. So whatever approach you choose, try to elaborate a prediction, try to elaborate your personal understanding of a system, because first of all, this is essential to check your model. And second, it allows you, this expectation allows you to compare your expectation with the model results. This is essential, okay? And in the case of coastal hydrodynamics and morphodynamics, this is particularly important because the system is very complex. Uncertainty is very significant. And therefore, it is particularly important that you don't trust the model blindly. And you will understand because we will make also an exercise, you will see that there is some subjectivity in the application of the model, which means, again, uncertainty. And therefore, my recommendation is, I already mentioned that last time, is look at the system, go there, try to look at the system, and if you have time, try to maybe monitor the system, if you have some time. Usually this is not the case, because engineers are called when the problem is urgent, typically, and usually you are given a very reduced time. So this doesn't help in order to gain a deep understanding of the system, but still you have to make a try. There is a say that, there is a proverb that says that engineers shouldn't design anything without having seen the site, without having, in a way, understood by a personal view the system. This may be not strictly true, because you know, now globalization means also that we may have opportunities to involve in the design persons that have never seen the system, but still, I think it is a good way of reminding us that personal understanding, observation, is an essential support to design. In this case, as I mentioned last time, we have waves interacting with the land, a land that is made by loose material, it's a beach. And the waves tend to displace this loose material, which means erosion, deposition. Deposition is also called accretion. So the effect of waves is not only erosion. We mention very frequently erosion because we are concerned by erosion. We are not concerned by accretion usually, because accretion means that the beach becomes more protected, becomes larger. But actually, these two phenomena occur together. If the sea erodes on one side, then there is accretion in other sides. So understanding waves is essential. Then, if I want to understand the system, I have to understand, on the one hand, the land, on the other hand, the sea. These two identities, these two entities that are interacting. So understanding the sea means that we have to understand waves, because if the sea is quiet, it's calm sea, you don't have any problem. There is no perturbation of any equilibrium. When we get waves, this is the situation where actually the sea and the beach interact. So we said that you are now going to study wave mechanics with Professor Archetti and Professor Bratt. And we recalled what are the essential behavior of waves we need. We mentioned this picture, and you said everything is clear here. So let me just recall, just 1 second, let's see if I can move forward. Yes, let me just recall. You will see with Professor Archetti this, maybe that you already have seen it. But let me recall that the waves are the effect of a random process. The waves are the effect of the wind over the sea. Just 1 second, because I have a student here. Student, can you hear me? Just 1 second, because I need to activate my audio. Can you hear me, please? Anyway, let me write on the chat. Okay. Thanks. So I said waves originate for the effect of the wind. So wind speed and duration is an essential driver of waves. And what matters is, besides wind speed and duration, the dimension, the size of the open water on which wind blows, and this is called the fetch. Okay, so the fetch. It's written there. F-E-T-C-H. It means the size of the open ocean where wind blows, and the sea depth is also important, because if the sea is very deep, there is no interaction of the waves with the sea bottom, and therefore it's only a matter of interaction between wind and open, wind and sea. If the depth decreases, then there is also interaction with the sea bottom, and we already mentioned that this interaction provokes the fact that the wave amplitude increases, the wave frequency increases, and the waves become steeper and steeper until they break. Okay? So the waves, especially if there is no interaction with the sea bottom, if the ocean is very deep, can travel for thousands of kilometers. So once they formed, even if they travel in a region where there is no wind, they can travel for a very long time. And this train of waves that travel without any more increasing effect of wind, these trains of waves are called swells, S-W-E-L-L-S. So you may get swells of waves even without perceiving any wind. How do the wave form? For the friction between wind and the sea. And wind conveys energy. Through friction, this energy is conveyed to the sea. And then what happens is that the surface of the sea starts going up and down. Remember, I already mentioned to you last time that waves do not imply a transfer of mass. It's only a transfer of forms. It's a transfer of energy. So it's the energy that moves in a given direction. Until they break. When they break, then we also have a transfer of mass. And we can see this because over the beaches, we can see the water that is running up and down, up and down. And this means that there is indeed a transfer of mass. But this transfer of mass happens only after breaking. So after breaking, we have this energy of the waves that is also transformed via transfer of mass. I am introducing some terminology, as you see. Let me just, first of all, let me just see if I have, okay, let me go back to the web pages because I have here a link that is interesting. And yeah. Here there is a link, sorry, I go back. The link is just below the figure. The nomenclature of beaches is introduced here, okay? Once again, if you see some broken links, I fixed many of them just 1 hour ago because I realized that some of them were broken. If you see some broken links, just send me an email and I fix them. So let's see this web page. I think it is useful because there is the introduction to many terms. So you see here the beach is defined here, the berm is defined here. We will recall what a berm is in a moment. the coastline, and I think there is also, let's see, we talked about the fetch. I don't see it here. Let me see. No, it's not here. And the swell, probably not, because this is for the coast, is a nomenclature for beaches. So the swells is a term that refers to waves and also the fetch. So it's not here. And but this page, anyway, it's useful because, or maybe here, no, there are no terminology for waves. Okay, let me just also have a look again at this picture, which clarifies what happens when the waves approach the coastline. What is interesting here, and I didn't discuss this last time, besides the form, last time, if you remember, I discussed the berm, the dune, and the bar, which you can see here, by the way. I just want to remind you that the bar forms where the wave breaks, and the reason is very simple. After breaking, you have a movement of water, as I said. Let me see again. So here we have the breaker line, okay? And after breaking, you have a movement of water that typically goes up along the beach and then comes back close to the bottom. And what happens is that some sand is brought back here. Some sand goes back here. It is transported by the water that is running back to the sea, close to the bottom. And then the sand goes down here and here. And then here there is turbulence. Turbulence created by the breaking. And then here we have the sand that gets trapped here and forms the bar. This is the bar. Okay, and this is called, I think there is the terminology here, the surf zone. You can see if this one, this is the surf zone. Okay, this is breaking. This is the surf zone, and this part of the beach is called the swash zone. Why swash? Because it's alternatively wet and dry. So this part that is reached by the run-up, this is called run-up, is reached by the run-up, and then also is affected by the run-down. This is called the swash zone, and at the end of the swash zone, we have the berm. This is the berm. Usually, besides the berm, you have a kind of a quiet channel. You may have it. So let me just continue here. After the berm, there is a depression, and then there is the dune. So in this depression, you may have some water, calm water. This is called the runnel. It goes parallel to the coastline, and here we have the dune. And I mentioned that the dune is very important for collecting fresh water and for sustaining ecosystems. What is interesting to point out, which is shown in this picture, is the time scale. So these forms, like for instance the berm, evolve on a seasonal time scale. Why seasonal? Because, of course, the position of the breaker line changes depending on the season. Typically, during winter, waves are higher, and therefore the position of the breaker line is moved backward toward the ocean, toward the sea. And the activity of the waves, the length of the run-up is longer. So the combination, actually, the result of these two changes, the breaker line that goes back and the run-up that becomes longer, the combination typically is a shift of the burn that is moved a bit landward and becomes a bit higher. And this is a seasonal evolution. The dune has a time evolution that is longer. The dune doesn't change the position any season. The dune may change the position due to shocking events, so events that occur once every 20 years, for instance, or 30 years, then the dune may be affected. And also the position of the dune and the dune itself may be affected by climate change, by even minor climate changes, sea level rise or whatever, or human intervention. But the time scale is usually longer. It's a time scale of the order of tens of years for the dune, unless, of course, it is removed by humans. But usually the natural time scale of evolution of the dune is of the orders of tens of years. And it's also, the bar is again seasonal. The time evolution of the sea bottom after the bar is again tens of years. So as long as you get into the ocean, the time evolution of the sea bottom is no more governed by sand transportation, sand erosion, sand accretion. It's governed by like tectonic forces or other geologic forcing, and the time scale increases. And when we are close to the coastline, there is still an effect maybe of extreme events that may move some of the material towards the ocean. So we say that the time scale is years, tens of years, like you see in the figure. And when you get very far offshore, then the time scale of evolution of the sea bottom becomes much longer, like thousands of years, as you see there. So it is important to get an understanding of these time scales, because also the model is expected to give a response that agrees with this expectation. Yeah?
In the picture, there is the berm until the limit of run-up.
Yes.
What is the difference between these 2 points?
Sorry, limit of run-up and the berm? Yeah, the run-up, basically, where you have the limit of run-up, which of course changes seasonally, what happens is that the sand that is transported by water, given that the water stops, goes down, settles down, and therefore it forms the berm. So
basically, they are on the same line?
Yes, the limit of run-up is at the basis of the berm. Okay, let me see, I think I have a picture here. You see here, the limit of run-up is clear, and you see the berm here. Yeah, it's very clear, and this is instead a dune, and you see the berm is over here, where you see my mouse, and the dune is just behind. By the way, this is a dune that you can see here also on the Adriatic Sea. If you go on a free beach, you can see this.
In this case, there is no runnel.
No, there is no runnel. No, in this case, no.
There is no
runnel. The runnel. Let me just see here. Runnel. Let's see images. I think we can find some image of the runnel. This one. This is very nice. Let me see.
Is it salt water or?
Salt water, yes. Let's see if. You see, the picture is titled Beach Runnel. See, there is the berm here, where I have the mouse. You can see the dune down there.
That's the dune, and the berm is the one between the runnel and the sea.
Yeah.
Okay, right.
Yeah. And let's see. This one as well, you see, this is a runnel. And it is a bit slow, but okay. This is a nice figure. You see the dune, the runnel, and the berm here. Okay, I go back to to the PowerPoint. These are the behavior of the waves that are important to us: amplitude, length, frequency, and wave direction. And Professor Archetti will tell you, and I already mentioned, the fact that usually we don't have a single wave traveling, because we expect like a situation like this one, sorry, I go back, like this one, where there is a single wave that is moving, actually in only one direction, and a single wave means that the amplitude and the wavelength, they are constant. It's not, actually very often we have like two trains of waves that interact. And when they interact, the effect becomes nonlinear. What does it mean, linearity? Let me be very technical. Linearity means that we can apply the superimposition principle. So if I had two waves crossing each other, and I could say that the resulting wave height is 1 plus 2, so the sum of the two wave heights, this would be linear, but it's not like that.
Because
Okay.
it's non-linear.
It's non-linear.
Okay.
Okay?
Because it's a pressure, so it's like sound.
Yes, it's like sound, yes.
Like the waves, not frequency.
Yeah.
So you need 10 waves to double the.
Yeah, I'm not sure it's logarithmic, but you made a good example. It's like sound, because sound actually is also an application of waves. Yeah,
Like waves.
yeah, yeah.
One is the fluid that's air, the other is waves in a fluid that is liquid.
Yes, this is,
For different density, but
yes, yes.
the effect we can imagine is can be similar.
Yes, it's nonlinear, and actually it's a very complicated nonlinear process, and therefore we make the assumption very frequently of linear wave theory, and Professor Archetti and Brat will tell you. Linear wave theory means that in practice we study, we assume that everything is linear, and in order to simplify further, we assume that we deal with a single wave. A single wave, a single plane wave. What does it mean? It means that, sorry?
Maybe. Like it's can be like, I don't know if we study with softwares, it's monodimensional.
It's monodimensional.
It's, you know, I studied with a bit of fluid dynamics, and like the equation Navier-Stokes for fluid dynamics, if we have more than one wave, so it's way more difficult.
Yes, yes.
Both for analytically by hand is impossible to solve it, but for softwares, just a monodimensional is way more easier to compute and to forecast.
Yes, I like this discussion, and let me just emphasize one thing that you said, monodimensional. This is 1D, this is essential. Yeah, 1D, what does it mean 1D? It means that if you take, with a plane on the wave crest, you cross the wave perpendicularly to the sea bottom and perpendicular to the wave direction, then basically the wave, this plane, as the wave travels, it travels parallel to itself. So basically, if I make a section, I have this wave.
Like in the picture.
Yeah, so let's cross with a plane, which is perpendicular to the sea bottom, and it's perpendicular to the wave direction. Then, as time passes, this plane travels forward and remains parallel to itself. Okay, and which means that basically the wave is not bending.
When we're studying, we have three axes in space. We're just studying translation on one axis.
Yeah, monodimensional.
So like this.
Yeah, monodimensional. Yeah, which means again, if you have the wave that is traveling along this direction, it's not bending. It's monodimensional.
It's not rotating. It's just translating.
Yeah, just translating. Yeah, this is called the plane wave, and there is a link here.
So the section is always like that.
Yeah, there is a link here. Plane wave. Let me see. Okay, here is the link. Let's open it. And here there is a definition. You know, it says a physical quantity whose value at any moment is constant through any plane that is perpendicular to a fixed direction. This is not really a definition. I mean, this is not a C definition. It's a general definition for any wave. But anyway, you can, and we are dealing with this. You see the wave fronts of a plane wave traveling in free space. So you have not, there is no change of direction. It's only one direction. Okay, good. PowerPoint. Okay, now, how can we study this? How can we study this interaction between the waves and the sediments? Not even, in our simplified configuration, the simplified configuration of a plane wave, how can we study this interaction? So this interaction is actually an interaction between sediment transport. This interaction gives a sediment transport. And the main assumption that we make is that the transport capacity and actually the sediment transport is proportional to the wave energy. This is our assumption. So it is reasonable. The more the energy of the wave and the more the sediment transport. Actually, you can understand that there are some simplifications in this assumption. And the first one, it's very clear. I mean, the energy of the wave actually means that the wave has a transport capacity, but this transport capacity ends up with sediment transport if there are sediments. So if I had no sediments, of course, I wouldn't have any sediment transport, even if I have a wave with high energy. So if we assume that the sediment transport is proportional to the wave energy, then we are also assuming that I have sediment availability to fulfill this, to satisfy this transport capacity. Okay, but the assumption is reasonable actually, and it's reasonable because, of course, with no waves, no energy, no sediment transport, and I can understand, because I just said it also, that if I have high waves, if I have very quick waves, I have more potential erosion. Why? Because it's more energy. Okay. And this implies that in order to translate this assumption into a model, I have to compute the wave energy, and in some way I have to relate this wave energy to sediment transport. But before I move forward, let me say, sorry, I just want to see if, what happens here. Okay, no problem. Before I move forward, let me just try to elaborate some more considerations on this process, to try to understand more. So first of all, sediment transport may occur in the form of bed load or suspended transport. I think that you understand the difference. The bed load takes place in the vicinity of the sea bottom. So the sediments move very close to the bottom of the sea. The suspended transport is formed by sediments who travel mid-height. They are traveling at any depth into the water, not just close to the sea bottom. Actually, we will see that we don't make any difference. We don't mean to understand, to make a difference between and therefore estimate separately the two contributions. But just keep in mind that typically the sediments with larger size are transported close to the sea bottom, and the sediments the finer sediments are transported at any height into the water column. Why this is important? It's clear because, I mean, the bed load can be stopped just by placing like obstacles, like walls, close to the sea bottom. The suspended sediment transport, in order to stop it, you have to put some obstacles that are emerging from water, like breakwaters, like groins. We will see what they are, okay? And a second important distinction, a second important consideration, sediment transport may occur along shore or across shore. Okay, along shore means that the sediments travel parallel to the coastline. And across shore means that they are traveling perpendicularly to the coastline. These two processes are typically taking place at different time scales and spatial scales. So the across shore sediment transport, the spatial and time scale are shorter with respect to the along shore. Because in terms of spatial scale, we already mentioned that we refer to the part of the sea and beach that is comprised between the swash zone and the bar, the breaker line, okay? And this is the spatial scale. And the time scale is typically that of a season or a single storm. Okay, so the cross-shore sediment transport usually undergoes big changes in different seasons and big changes between the storm event and the normal situation. The longshore sediment transport may take place over very long spatial scales, so sediments may travel for hundreds of kilometers, and the time scale is a longer time scale. So the driver of the along shore sediment transport is not a single storm event. It's like a long-term behavior like currents, like currents that may last for a long time. Okay, this is important because actually here we make a difference. So our models and our defense for coastal preservation, coastal recovery differ depending on the two types of sediment transport. Typically, let me just make a figure here. Typically, the protections for the cross-shore sediment transport are placed parallel to the coastline. You understand why? Okay, because let's suppose that we have a coastline here. And we have the sediments moving in this direction, which is across shore. Then, if I want to stop this process, I should put a protection here, like a wall, or rather than a wall, I could put boulders, aggregation of boulders, and this is called breakwater. Did you study breakwaters already with Professor Archetti?
No, not yet. We have done only one lesson.
Okay. I think I have figures, but let me just check very quickly. Breakwater. Yeah. Correct. And let me just focus on the right image, because here it's not easy from this group of I don't see any very nice figure here. Just one sec. Okay, here we are.
Otherwise, on Google Maps, there are in front of Ravenna.
Okay, interesting. Just one second. No, just one second, because I don't understand why. Let me see. This is a nice figure. Let's see. Okay, this is a nice figure because you can see the breakwaters and it is now loading. But what's interesting here is the effect. You see that the beach behind the breakwater, behind means between the breakwater and the land, moved forward. Okay, so the size of the beach increased for the effect of the protection. These are breakwaters, and there are many pictures that you can find on the web. The longshore sediment transport instead occurs along this direction, and if you want to stop it, you have to put a protection that is perpendicular to the coastline.
So the protection must be perpendicular to the direction of sediments.
Yes, correct. And this is called groin. Groin or groin with a Y. I am using both versions in my lectures. So we make a difference, and very often they are coupled. Sometimes they are coupled because, you know, we like classifications, but actually I already said that what happens in practice is a mixture. And therefore, when there is concern for erosion, they may be coupled. And there are pros and cons in terms of side impact of these protections. And first of all, they are not very nice to see. They look not natural. And therefore, we tend to use boulders because they are more, they are cheaper, and they are also more environmentally friendly. Also for the fishes which can, which can live in the submerged part of these protections. And in particular, breakwaters are particularly disturbing for the visual because we have to take into account the touristic value of beaches. And the breakwaters give the feeling that something is, it's unnatural, it's artificial. And because they take the visual, you don't see the skyline from if there is the breakwater. So in some cases, we use submerged breakwaters in order to limit the visual impact. Of course, also their efficiency to stop the across-shore sediment transport is reduced for obvious reasons. The groins, from the point of view of the visual, look more disturbing. On the other hand, they interrupt the continuity of the beach. So people that like to walk along the beach, and they can walk for several kilometers, or people who like to jog along the beach, they don't like the groins because it's an interruption, and you can continue to walk. You have to go inside and pass by. And so for different reasons, they are impacting. But on the other hand, of course, we need to live with the environment. We need to reach a compromise, and therefore, of course, depending on the local context, on the local situation, we have to choose the best solution. Okay, now let's talk about the model to estimate the sediment transport. What do I need to estimate? I need to estimate the volume of sediments that is transported per unit time along the beach or across the beach. Volume. Why volume? Volume because if I knew the volume of the sediment that is displaced, I can, by introducing additional assumption, predict how the beach will evolve. I repeat, if I knew the volume of the sediments that are displaced per unit time along the beach or across the beach, if I knew it, the volume, I could predict the evolution of the beach in the future. I try to explain better. First, this assessment is local. So I cannot make an assessment that applies to 100 kilometers of beach because the conditions change. The wave height, the wave direction, and the size of the grains, the conditions change. And therefore, my assessment must be very local. So I take a delta of the beach. Okay, this is a delta S. Let me call with S the coordinate, the spatial coordinate along the coastline. So I take a delta of this length of coastline, which must be reduced. It cannot be very large. And then I estimate here the volume of sand that is eroded. Once I know the volume, let's suppose that it's a minus volume, so something that is subtracted, I can predict that next time step, the beach will move here. How? We will see. Okay? And if in the next delta I have a plus, it means that this volume that was eroded here is displaced here. So I take a finite difference approach. I think you are a bit familiar with numerical modeling. Numerical modeling, it means that when you have a system that is very heterogeneous and cannot be described analytically, we solve piece by piece by taking a finite difference approach. So I have typically differential equations which apply to each delta. This numerical modeling involves an approximation, and you can see it here, because of course the resulting shape of the beach cannot be made by steps. So what will happen here, it will be something actually, in the reality, something like this. Okay? But the effect of the numerical approximation gives a representation by steps. Of course, the effect of the approximation increases if the step is large. If I adopt very small steps, then the approximation is improved. Okay, so let's now find an analytical relationship then, which gives to me the volume of sediment that is transported per unit time. I already mentioned the basic assumption. This volume is proportional to the energy of the waves. And it's written here. And this formula that we use that is based on this assumption is called the CERC formula, or CERC, okay? And I don't remember the meaning of this acronym. We will go to the web pages, it's written there. This is a formula that is widely used. And you see the assumption is the second bullet point. Let us assume that the total longshore or alongshore, they are synonyms. Sediment transport rate is related to the longshore component of the energy flux, which is generated by waves that approach the shore at an angle. Let me explain better. And let me draw another coastline. If I have a coastline here, typically a plane wave, approaches the coastline at an angle. What is this angle? It is the acute angle alpha between the wave direction and the coastline. So if I have in this wave direction a cross-shore component, I may expect a cross-sediment transport component. If I have in a longshore component, in the same way, I can expect a longshore sediment transport. Now, the CRC formula deals only with the long-shore sediment transport. Let's forget about across shore for now. So I am interested in the component, in this component here. And of course, this component is given by, so the perpendicular component is given by, I can say that the wave direction is the longer, it's the longer side of the triangle, which is a rectangular triangle. So the longshore component is given by the energy of the wave along the wave direction times the cosine of this angle alpha.
Should I turn on the light?
Yeah, and thank you. Okay. Now, let's indicate, and let me see, with the symbol EB, the wave energy density per unit horizontal area at the breaker line. First, I am interested in the wave energy at the breaker line because this is the point where sediment transport begins. So I refer to the wave energy at the breaker line. And now I want to compute this wave energy density. Why density? Because it's per unit horizontal area of sea bottom. And now, it may be difficult for you to understand why I refer to unit horizontal area. Let me just move forward and you will understand. Basically, I am interested in an area of sea bottom, so I need an energy density that refers to the sea bottom. So I take the energy of the wave per unit area of sea bottom. And I will show you just in the next slide how this is computed, and when you see how it is computed, I think you will understand better. Okay, let me just call for your attention because the derivation of this formula, it involves some math. It's not difficult, as you will see, but it involves some math and maybe some reflection later on to fully understand what's going on. You never computed before the energy of a wave, correct? Okay, very good. No, it's better. Okay, so there are two components in the wave energy. There is a kinetic and a potential component. Okay, and the kinetic component is given by the up and down movement of the wave. So the fluid particles that are traveling with the velocity. And after the breaker line, the kinetic component is actually given by particles that are traveling along the sea bottom towards the beach. And then there is a potential component, which is given to the position. Okay, and now I think it would be nice if I showed you a graph of, for a plane wave, of how this kinetic component and potential component combine. So I have a link in the web pages, which is nice. I think it's better if we look at it soon. First of all, in my web pages, you can find a table which gives long-shore transport rates from US coasts. It was 40 years ago, and it's still valid. So you can see that it is indeed something very relevant, and this transport rate are cubic meters per year. So you see that if you look at the higher values, we get close to 1 million cubic meters per year in some part of the coast, and I mean it is relevant, and we are talking about important volumes. Of course, in the ocean, it's higher than in the Mediterranean, but still, even here, it's an important phenomenon.
Sorry, if it's 1 million cubic meters in 1 kilometer of beach.
It's basically, if you fix a section on the beach, it means that in 1 year, it passes 1 million of cubic meters through this section. So
which is the section, the thickness?
It's a location. It's a location. It's not a matter of thickness. You have like a current that passes through this location, and it doesn't imply an extension, and it refers just to one line, to one point, and you have 1 million of cubic meters per year moving, and here there are some probably some details, but I am sure that this is the meaning. Okay. Okay, so let me see, just 1 second. Okay, I think maybe this is the link, just 1
So
second.
it's a movement parallel to the shore?
Yes. So,
okay.
Okay, so like I stay here for 1 year.
Okay.
I'm sitting here, and what I see is a volume of beach passing on the beach.
Okay.
Which means that if you place a groin here, you may expect during 1 year to get 1 million of cubic meters accumulated against the groin. And downstream, it means that you don't have any more flux and you may have erosion. So I anticipated what is the effect of a groin. You have accretion upstream, I should say updrift, and downdrift, you have erosion. Okay.